with the velocity field, we may now go ahead and find the average velocity. So the average velocity is defined as u bar is equal to integral u dA upon integral dA. So if we assume a unit width, or let's say we assume a width b into the plane, so this becomes simply integral minus h to h u dy times the width divided by 2h times b. So then b can cancel from both. So this becomes 1 upon 2h integral. So integral of minus h to h u dy. We recall the velocity profile that it's parabolic. In fact, let me just draw it over here. So because of the symmetry, we can simply convert this integral from minus h to h as an integral of 0 to h, but twice of it u dy, and this 2 also cancels. So this becomes 1 upon h integral 0 to h u dy. So this is 1 upon h integral of minus 1 upon 2 mu dp star upon dx, where this is known to be a constant, times h square 1 minus y square upon h square dy. And this integral is from 0 to h. Let us say y bar is equal to y upon h. So we can write u bar as 1 upon h integral 0 to 1 minus 1 upon 2 mu dp star upon dx. So this is h square. This becomes 1 minus y bar square, and this becomes dy bar times h. So this h cancels out. So this becomes 1 upon 2 mu dp star upon dx h square integral 0 to 1 minus y bar square dy bar. Now if we focus only on this particular integral, this is 1 minus 1 upon 3, this is 2/3. So if we substitute the numerical value, we obtain u bar is equal to minus 1 upon 2 mu dp star dx times h square times 2 upon 3. So this 2 cancels out, and essentially the average velocity is 1 upon 3 mu dp star dx times h square. Let me just quickly write down the velocity profile over here. So u is minus 1 upon 2 mu dp star upon dx h square times 1 minus y square upon h square. So now we can write down the velocity in terms of the average velocity. So u upon u bar from this expression comes out to be minus 1 upon 2. So this 1 upon mu dp star dx h square and 1 upon mu dp star dx h square, that will cancel out when we divide. So all that will remain are the numerical factors. So it's 3 goes up, and it simply becomes 1 minus y square upon h square. So essentially it's 3 by 2. So this is the expression for u upon u average. Now what is the maximum velocity? So the maximum velocity occurs, if we recall the velocity profile, it's a parabola. So the maximum velocity occurs at y equal to 0. So if we substitute y equal to 0 over here, we will obtain u max upon u bar is equal to 2/3, and that means the average velocity yeah. So the average velocity is 2/3 of the maximum velocity. Now if we proceed further, we can find out an expression for the shear stress at the wall. So the wall stress is essentially tau xy at the wall. Now because it's a unidirectional flow, by a unidirectional flow, we imply that the flow is in one direction only. There is no two-dimensionality in the flow. So this will simply be equal to mu del u del y at y equal to 0 because the wall, or rather y equal to h. The fact is, the stress in general at a wall would have been del u del y plus del v del x. Essentially this is tau xy, but because v is 0, this other term would vanish. So this becomes mu. So then we have minus 1 upon 2 mu del p star, or rather dp star dx h square. So now the derivative of 1 minus y square by h square, it would be minus 2y upon h square, and we will evaluate at the walls. So the walls are located at y equal to plus minus h. So this mu cancels out, this 2 cancels out. So this becomes dp star dx. So this h square would also cancel out, and depending on which wall we want to find out the stress, it will be h. So we focus on the magnitude for now. So the tau wall would be this. So in terms of the average velocity, what is the expression for the average velocity? Is it this? So what is dp star? So if we rearrange this expression, u star, rather u bar is minus 1 upon 3 mu dp star dx times h times h. So dp star dx times h becomes u bar times 3 mu upon h. So this is equal to minus dp star upon dx times h. And because we are more concerned with the magnitude of the wall shear stress, this essentially would boil down to this particular term, 3 mu u bar upon h. And just verify whether the dimensions are correct. The dimensions of stress are in fact mu u upon h. So this checks out. We can proceed further and express the wall shear stress in terms of the skin friction coefficient. So the skin friction coefficient is given by Cf. It is equal to the magnitude of the wall shear stress divided by half rho u bar square. So it is a sort of measure of the shear stress to the dynamic pressure. So this becomes 3 mu u bar upon h times 1 upon half rho u bar square. So this 2 goes up, 6 mu, so one of these u bars cancels out. So it is rho u bar times h. So we can write it in terms of the characteristic height. So the characteristic height of the channel is 2h. So the channel height, the distance between the two parallel plates is 2h. So this becomes 12 mu upon rho u bar 2h. We can define the Reynolds number as the density times the average characteristic velocity times the characteristic length upon mu. So we'll come into the discussion of what the physical significance of this number is, but for now it is sufficient to know that it is the ratio of the inertial terms to the viscous terms. It is sort of a measure of how viscous the flow is. So it is defined as this. It is rho UCLC upon mu. So this becomes rho. So the characteristic velocity is going to be the average velocity. The length, the characteristic length between the two parallel plates is going to be 2h, and the viscosity is v. So if we substitute this, this comes out to be 12 upon the Reynolds number. So this is the Reynolds number based on the average flow velocity and channel height 2h. See, there is no universal way of defining a Reynolds number, and you must specify what the Reynolds number is defined on. So this gives us an expression for the skin friction coefficient, and because it's a dimensionless number, it eventually comes out in terms of a dimensionless number. You can verify yourself that the Reynolds number is in fact dimensionless.